Thank you very much for the for this conference. Thank you, organizers. It's always nice to be here. Great place. I will start with a warm-up, just maybe to set things up. The warm-up will be on standard deformation theory of associative algebras. I'll wrap it up in something scientific, something like stacks, but after all, yeah, as Grothendieck tried to teach us, that's how the algebraic geometry has to be done. So, yeah, we have this groupoid, but rather two groupoids of associative algebras. So each time we pick a commutative ring, use it as a base, and we could just look at these two groupoid objects, associative algebras over K. Morphisms. So in the simplest incarnation are just homomorphisms. Algebra homomorphisms. And yeah, you could stop here. We could stop here, but yeah, you'll see that it's not natural. It is more natural to consider two cells between those which intertwine in a natural way. So yeah, intertwiners, I'll call them. At any point when something is not clear, please interrupt me and demand clarity. Sorry? Yeah, so yeah, homomorphisms are automorphisms. Because yeah, I want to go for it, yeah, invertible. So intertwiners also invertible elements in the target, which make so like invertible element R, which make this true point X, where F and G are two isomorphisms between two different algebras. So yeah, that is that is what we can think of as some geometric object by just varying K. So we have a functor from commutative algebras to the two groupoids. Yes, please. Yeah, so two stack is just the a bunch of these associated to all commutative algebras, plus some nice gluing conditions which are not essential effectively for this deformation theory. No. So two stack is a functor from commutative algebras into two groupoids. I do have a functor here, right? So for any K, this is a two groupoid. But yeah, I have a collection of them varying nicely. So first of all, it's a functor, but then it's not just an arbitrary functor. It's really what is called two stack because of some nice gluing properties. This functor, what's called two stack. Yeah. Two stack is first of all a functor plus blah blah blah, and the blah I'm not really interested in because of the purpose deformation theory is really very local. So I have to have very little from this functor for the rest to work. No, yeah, different, but they're isomorphisms. So yeah, F and G are yeah, okay. The typical pictures. So we have R, we have S, both K algebras associative. Then we have F, and we have G, and then we have this two cell, which is called R, and that is what. So R is an invertible element. In S, F and G are isomorphisms, and then the condition for the two-cellness is this. Sorry. Yeah, but that is packaged now in the functor part. Yeah, that is packaged into functor part because of, again, my purpose to deform. So actually to frame deformation theory in this language. Yes, please. They both are in the same place in S. So this is for any x in R, but yeah, this is inside S. Both. So f of x is inside S, g of x is inside S. So the yeah, yeah, I'm just multiplying inside S. Yeah, so this is inside S. This is inside S. So this is inside S. This is inside S. The product are inside S. Yeah, no, R isn't just an element. Yeah, okay, I could say it better. So instead of this, I could just take a billion categories. And then to relate, I have to take an algebra and turn it into a category of its modules. Okay, so then this will become functors, equivalences. I might have a bit more equivalences, but again, for deformation theory, it's not really important. And this will become natural transformations between those equivalents, irrotable natural transformations. So maybe I just should write this instead. So it could be like, bless you. So that will be a billion categories. K-linear, then again, equivalences with all the attributes. And then natural transformations, natural isomorphisms. Okay, so that's just a kind of like an easy thing. Okay, yeah, thanks. So, so what is this usual deformation theory? Usual deformation theory, right? We just, okay, we have multiplication, it's commutative. Yeah, so kind of like getting Y algebra out of polynomials. We just deform it in sort of perturbation theory, but yeah, we just started the first term. We write multiplication as sum of the original, say, commutative thing, and then next term. Deformation parameter is just squares to 0. What should I call alpha? So mu 0, and alpha, they're all binary maps, operations on the underlying vector space of the algebra. And then just writing down the conditions for that to be associative again, we get what now we call Hochschild two-cycle condition. And the same happens when we deform identity automorphism of any algebra, again by adding some term. And then the condition for that to still be an automorphism or in homomorphism is that alpha is a derivation. So that's what I'm packaging into the statement. And if you don't like this packaging, please interrupt me, please demand unpacking. So the tangent, and automatically a billion to stack of that, yeah, we have to pick up a marked point, some algebra. So what it is, just to say how to see it in terms of these groupoids. So we'll just take an object there, and I will look at all. Yeah, first of all, we have to enlarge the ground ring to these dual numbers allow this epsilon. So epsilon squares to 0 everywhere, unless specified. Now we'll look at algebras there, and then we'll look at all which sort of go to R. So we'll look at really kind of like a two-groupoid fiber. But yeah, what is literally done? So we have like an algebra here, and then we say that its reduction is isomorphic. Yeah, it's category theory. Everything has to be specified. Isomorphic to what we picked. And then morphisms are homomorphisms which make it compatible up to intertwiners. So we have triple over dual numbers with k. So it's just reduction, just killing a epsilon. It's, yeah, forgetting epsilon. So forgetting epsilon, we have this and that. So then, yeah, then homomorphisms, it's really everything. So homomorphism is, we have S, we have T, and the condition compatibility is that reduction of isomorphism has to be compatible with this, up to intertwiner, and then intertwiners of these two cells of that tangent stack. And it becomes abelian automatically, and being abelian, it's nothing but a really short chain complex, and this chain complex, of course, is well known. So this abelian stack in its chain complex form, I'll write here. So this is 0 level. Okay, it's just something which is built out of a chain complex, chain complex of length 2. Yeah, if it helps. Sorry. So the source and target are captured by this differential. Yeah, three-tone complex. I have to cut it like that. So the top is the cocycles. Cocycles in the standard Hochschild complex. So this is just from the computation, from this computation, which we all know and love, right? When we spell out what is for that to be associative, alpha has to satisfy certain equation, and then what is for this to be multiplicative, again, phi has to satisfy a certain equation. These two equations kind of like talk to each other, what Hochschild found in a way of a complex, and it continues. So there is higher terms, right? And yeah, who ordered them? So why them? So you could say, oh, okay, abstraction lives in the cohomology, but yeah, okay, abstraction is not visible here. We have to allow epsilon squared to survive to see abstraction. Yeah, maybe you could say that, yeah, it's an infinity where you will see all the other degrees. So if I replace associative algebras by its right homotopy invariant version, the infinity algebras, then everything will become good. And okay, yes and no. So if it's ordinary Z graded infinity algebras, I will only see a sort of a narrow part, graded part of the Hochschild complex. There is, of course, a way of remedying that by allowing, by taking Z2 grading, but then I will have to see my complex several times. So yeah, there's some hiccups, you might say. But that's only the beginning of hicking up, because this Hochschild complex, as complexes do, they compute extensions in some other abelian categories. And what is this all to do with the deformation story? So I'm basically full of questions. The talk is full of questions. It's not really like a end point in any way. So these sorry? Yeah, I'm just going to write. So, as extensions, Yeah, that's what the original Hochschild's, so Hochschild's origin was, computing extensions. And again, sweeping relativity details under the carpet. It's just extensions in the category of bimodules. That's what Hochschild complex computes. Well, the part of it, the extensions between the monoidal unit object with itself. And okay, so this this is the extensions of our bimodule. Okay, yeah, so the easiest way is just, it's a not so short exact sequence. And then there are terms. And the length is determining the number here. And then you, sorry? Yeah, and then you have to identify them by collections of morphisms, but you require that at the end points what you extend and what you extend by, your compatibility morphisms are bijective or equality. Exact sequences, yeah. Of bimodules. But yeah, now people don't say that. They say, okay, you write a projective resolution of that in the category of bimodules, and then you apply Hom factor, and then you compute it. Something which measures non-exactness of Hom factor. But sort of, again, original definition was like that, so that's why they're called extensions. But no one really messes up with those anymore, which is a pity. So yeah, what is one to do with the other? Why? But these two sides, they contribute different things. So for example, if we look at the next order deformations, if we look at tangent cone, but in the quadratic sense, just looking at the next order. So here I will be brief, but again, what does it mean? It means that we allow epsilon to appear in the square as well. So just, okay, we looked at this geometric object of all our associative algebras sitting at the point which is called R. We have this direction called alpha, and can we really move along this direction? And that is what the first abstraction theory is responsible for answering this question. And geometrically, that will be just looking at the tangent cone. So yeah, we have this tangent space, but not all directions are really allowed. And those which are really given by some sort of system of quadratic equations. And again, we know from the work of Gerstenhaber that in the associative algebras, that is controlled by Gerstenhaber brackets. So this is defined by and again, sort of looking at the small degrees, this is some interesting sort of structure, and really don't see the bracket as it is, but you see kind of like the quadratic portion of this bracket, so the bracket of something with itself. But yeah, okay, for these guys, really just the Lie brackets on derivations, because these guys are nothing but derivations. And They are non-abstracted, so you can extend them to all orders. But yeah, their composition, their group structure is described by this Lie bracket, which is the Lie bracket of derivation. So this is a part of this Gerstenhaber bracket on the Hochschild complex, on the standard Hochschild complex. But yeah, we know that this is, okay, this is only the beginning, and the Lie bracket really is a part of bigger structure, which is L infinity structure. So we have to think of higher sort of components of this higher brackets, which might exist for bad choices so far. And this is one sort of interesting structure on the deformations, but another interesting structure comes from this. So from extensions, we have a natural operation of gluing these extensions, the two extensions. If they start and end in the same place, they can be glued. This is called unit product. So far, no. Anyway, why should I? Sorry? I'll just worry about it. Yeah, it will be ugly, but it's still there. Sorry? Yeah, and so yeah, so far anything. Yeah, I'll have to say when. Yeah, but probably not today. Luckily, I don't have to remember about such things as characteristics. The Yoneda product on extensions corresponds to what's called K product on. Yeah, okay, so you have one extension, so boom, blah, blah, blah. You have another. Okay, I have to write extension, this is E0. And it ends at R, but then I take another extension which starts, sort of, yeah, if you read from this way, extension length M, and then again it continues. Yeah, but you know, you just glued it like that. You take the composition, and then it becomes exact. Then it becomes exact of its own. So that's called, you know, the product of extensions. It's, yeah, that's why extensions are so good. You see stuff. It's all on the surface. Well, K product is just some like operations on cochains. Yeah, you can, but again, it's easy operations. So you have a Hochschild cochain. So you start with many copies of R, go to, and then you have another cochain, many copies of R. You just use multiplication of R. And from above, it becomes, again, it is compatible with the differential. So if you take two cocycles, it becomes a cocycle again. A miracle. But yeah, it's not a miracle because of this, really, because of the correspondence between the two. Sorry, where is the? Yes. Yeah, so yeah, K product. The K product of standard on the standard Hochschild complex. This doesn't talk much to the deformation theory. So yeah, if you take the derivations, you take the K product, that becomes a two-K cycle along which you can deform your associative multiplication. But yeah, derivations are deformations of infinitesimal symmetries. It doesn't make sense if you start trying. Yeah, at least it didn't make sense for me when I start trying to do that. Just all kind of like running away. But it is there, so it is there for a reason. I don't know the reason. But yeah, it's just, again, a baby example of things which will have to appear. Yeah, I'm running out of time. If I start talking about deformations of tensor categories. So tensor for me is very sort of, yeah, it's not what is usually meant by, but yeah, it's k-linear, not even a villain, just k-linear category together with the monoidal product, and the monoidal product is k-linear. Yeah. Yeah. So maybe I shouldn't start with all this stocky business and really, but yeah, maybe I will. I will, but just I will have to spell out at least things here. So again, it is the geometry of this tensor category. So we want to deform a tensor category, whatever it is. So we want to see where we're deforming. So there's some space, generalized space of such, and the easiest way to describe the space again is through the functor from varying commutative basis. So whatever scales you are choosing, two groupoids and two groupoids of tensor categories. So again, of a chosen base, objects are these tensor categories. K is commutative ring. Tensor category is, okay, it's k-linear category where you have monoidal structure, we have tensor product. So you have the tensor product, you have the k-linear, meaning that home spaces, you could add morphisms and multiply them by elements of k. That's k-linearity. As MacLean taught us, we shouldn't write home, just write C and then two objects, and that's short notation for the home space. And then, yeah, it's a K vector, K module. Assuming free. Again, for the purpose of deformation theory, it's enough. And then there is a monoidal structure, so that is a functor from Cartesian product of this category into itself. So I have something which is denoted like that, and I have associativity constraint. I might or might not have unit, monoidal unit, that's just, yeah, extra. But I have associativity constraint, and it satisfies the pentagon axiom. Probably should write it down, okay, yeah, because it's going to be important eventually. So, okay, associativity constraint is an isomorphism for each choice of objects x, y, and z between tensor products like that. So we don't think about it when we look at our model example of vector spaces or K modules with free K modules with the tensor product of K. Just comes for free, right? But if you think about the definition, okay, how do you define tensor product? By universal property, then it should be there. Well, by universal property, you don't even have the tensor product. It's something which solves the universal property. But you usually have a model, so you have a big sort of K module and a quotient by a subspace. And then when you do these two things in two different orders, you effectively end up with two different answers, but they're canonically isomorphic is just forgetting brackets on tensor signs. But still, it pays off to remember it. That's what, yeah, basically category theory is, just remembering a bit more of how things are identified. And this collection, we have it for any choice of x, y, and z. This collection has to be natural. Again, this is the biggest message of category theory. Natural things are natural in the categorical sense. For any three morphisms between x and x prime, y and y prime, z and z prime, you have a commutative diagram. That's what naturality is. So you have this natural collection of isomorphisms, and then it has to be not an arbitrary thing, but has to talk to each other in a nice way. So what do I mean? From now on, I will suppress tensor signs. If I have now 4 objects chosen, and then how many combinations of brackets I can put on? Yeah, Catalan number 4. Answer is 5. So here they are. Each two, not each two, but some are connected by an instance of that. So that has to be commutative again. The choice has to be nice in the sense that it commutes. Yes, please. Yeah, so it is to stack. I have to finish this list in here, right? Yeah, no, honestly, it should be 3 stacks, but this sort of the last level usually decouples. So, so tensor categories. But yeah, actually, the last level is kind of like cryptic, but okay, it is there. So tensor categories, the tensor equivalences. Tensor natural isomorphisms. And then something else coming from sort of so for that I need to allow the monoidal unit object, and then there is something else. So with the unit object, monoidal. I really have like internal scalars. Internal scalars of the category, and they usually they just pass through, and then the differential in the tangent. But yeah, we're jumping ahead. So sorry, I'll have to get to it in a natural way. Sorry. Okay. So what happens if you drop it? If you do something else, things just become unreasonable. It's a fact of nature. Without it, things become unreasonable. There is no, No, I'm not dropping associativity. Up to isomorphism, but yeah, I'm not really dropping it. I'm really recording it. I'm carefully recording it. So it could sometimes it could be identity, and then the category has a name of sort of strict monoidal. And any category can be made such. That's the beauty of this the fluidity, flexibility of categories. But that's not what we need to do. So when it's like squeezing in one place and blowing up in another. That's this sort of strictification. We will have to change the category, at least in its form, in its presentation, to make it strict. But yeah, okay, an example perhaps. That's what is good for seeing it. So let's look at the graded vector spaces. In vector spaces, we don't have anything interesting coming. But let's look at the graded vector spaces by group. The easiest group next to 1 is 2, or for the 2, and there's only 1. Let's look at the category of the graded vector spaces. Vector. The tensor product is as of vector spaces, but a good thing, we can make it graded, right? So how do we grade? By multiplying degrees, right? So degree 0 will be coming from 2 sources, like 2 things in degree 0, but we can take 2 things in degree 1, and it will also give us something in degree 0, right? So there's a tensor product. There's monoidal structure in this category. And there is, of course, a usual associativity, which really just does nothing. But there is another interesting solution of this associativity coherence of this pentagon, which has the following form. So we take UVW. I'm defining it on decomposable tensors. And then, yeah, we do rebracket as in vector spaces, but yeah, we could introduce a phase. Am I doing this right? Yeah. No. Yeah, I'm doing it right. So that is, yeah, I'm trying to, yeah, that's correct. So that again, that's the beauty of that too. The Tricker cycle is the only one, and it's just like, you don't have boundaries to it, so that's the Tricker cycle. You just take the degrees and multiply, so you have to have all the degrees 1 for that minus sign to appear. Yeah, okay. If we look at all groups and solve the same problem, it's easy to solve. Solutions for this pentagon, they correspond to group cocycles, 3 cocycles in coefficients, whatever scales we have. Trivial G action. Okay. Deformations is just, again, the deforming something in here. So we take a category and we look at the first order infinitesimal neighborhood of that geometric object. That's scientifically speaking, but what really we are deforming in here? This thing. That's what we're deforming. We're just, again, expanding this thing. But rather than writing it like that, it's better to write it as kind of like the original. Yeah, I'll use twiddle for the deformed. The original associativity is multiplied by something invertible. But just for cosmetic purposes, that is just for that to be an endomorphism. So that will be starting in this object and ending in this object. Again, will be natural collection of such endomorphisms, because the result has to be natural collection. And then the pentagon equation corresponds to some system of equations for some equation on these natural endomorphisms. So let me introduce a notation for this natural endomorphisms. The endomorphisms of I'll just call them pivot endomorphisms of the identity factor of C, just of C. And if we put this template at every instance of our pentagon, let me write it down, the labels. So there will be X, Y, and Z, W. So that W is just one object in this case. So now we are treating X and Y as one object, W. Here we have alpha on Y and Z and W, and we're not doing anything to X. X is like outside. Alpha X, Y, Z, W. And here, alpha X, Y, Z, and then W is not used. So if we put this template into each of those instances, and then expand the equation, which is the equation between this composite and this composite, and then yeah, remember that epsilon squared is 0. So what we have is the following. Yeah, let's do it together. So the first contribution is A. I'm running out. With X and Y and ZW together, we'll just add, right? That's what deformations do to us. They solve complicated equations where we have compositions and all that. It all is turned into linear equations. That's Newton, right? Linearized. So this is the first contribution. Then the next will be A X Y W. That is the top. The bottom is and okay, and that is the something which is in this tangent abelian stack, but yeah, something corresponding to the top layer. Third co-cycles of the category. Stack is a stack for a reason, because yeah, we have things identified by monoidal equivalences, and then we have to solve the following problem. Yeah, we have two such deformations, two solutions of this three co-cycle equation, but we have an identity functor perturbation of it, which makes them the same. Right, so the tensor categories are compared by functors together with the tensor structure. So tensor functors, things which compare and allow us to say that things are the same, which compare tensor categories, things like that. Again, it's sort of inevitable. You have to compare tensor structures. So how do you compare? Okay, this is this recording the multiplicativity of the functor one way or the other. So let's do it this way. So you have the collection, natural collection of isomorphisms like that. But then again, it's not, if it's just an arbitrary one, there will be troubles, but it has to be coherent. So the coherence is, okay, I will suppress tensor products as before. Take 3, and then, so these three can be rearranged using just associativity in the first place. And, but then we have the tensor structure of the functor to break it down to things. And then, yeah, this is just algebra, right? On steroids, just recording every little sort of, yeah, this is for mild Asperger's, recording every little things, but that appears in physics, that appears in nature, that appears in condensed metaphysics, that appears in really sort of like experiments. How do I know? Yeah, so the first, I think the first experimental instance, yeah, it's a fractional quantum Hall effect. So you have this sort of strange discretization of the Hall current in the semiconductor sample in the strong magnetic field. So. Yeah, first of all, it appears in high energy physics, but it was theory. So that is modular categories. You just try to carefully record representation theory of rational conformal field theory of vertex separator algebras of those, of chiral algebras of those. And then something where you have to have these 6 J symbols. So there's no identity solution anymore. First of all, the sort of the of that, yeah. So for your concrete representation theory, tensor product is really strange. It's not something underlined by tensor product vector spaces. So there's no identity solution. There is nothing to like grab on. But yeah, the solutions are there, and they are these 6J symbols, and they're strange. Well, they were strange. So okay, just completing this algebra. The brackets here, and then different set of brackets here. Oops. F of y, f of z. And here we use different associativity in the target, and that's the way of comparing them, really. And again, if we record everything, if we take as f the identity functor from C to C, and if we take the sort of trivial solution, the identity solution for that tensor constraint, and expand it, then what we have, maybe I should write things so that it will become visible. Maybe it's better to say this rather than complicated stuff. So here I'm using associativity in C in general. Here I'm using associativity, still call it A, but it will be associativity in D. And I need to call this, so call it phi. Yeah, exactly. So I'm going to write the co-boundary equation for this cycles. That's what I'm trying to do. I'm going to pull it out of the same Stucky problem. Okay, I have two deformations, but maybe they're the same in disguise. And this is the disguise. This is allowed disguises. So just changing coordinates. Yeah, you're right. Sorry, alpha. Alpha is what I mean. I do apologize. Alpha, yeah, A will come as a perturbation of those. Thank you so much. So phi is this collection. And that's what comes inevitably. This coherence, again, is something which you can't avoid, and there is only one thing you need to ask. Everything just falls out of it. It's another coherence sort of. Yeah, the same happens with pentagon. We demand pentagon, then yeah, all diagrams we can write using phi and tensor product, and identity will be automatically commutative. The same with this. So that's called coherence theorem, Maclane's coherence theorem. Okay, again, now deforming this, but deforming it in the case when f is just identity functor, so I start and end in the same C, which I happen to have two deformations for its associativity. So I have A and A prime, that's what I'm now comparing. So here I'm deforming with A, and here I'm deforming with A prime, and then so phi is of the form something. So new phi is of the form original, which was just identity with this sort of perturbation, and epsilon is a parameter square into 0, deformation parameter. So then again, writing this as a linear equation, we will have on one side, on this side, we will have the A prime. F doesn't do anything, it's identity. But then we'll have this psi, why is that? Is identity on X, and then psi X, Y, Z. That has to match A, X, Y, Z, plus psi, what is it? xy, comma z, c, x, y, doing nothing on z. And again, natural from deformation theory comes this. And it is a complex. It is differential in a complex. And you can continue it. So that's what I call deformation complex of a category, and what is responsible for deforming categories and sort of functors between them. So there are three terms. Number one, number two, and number three. So here we have to take the co-cycles as before. That's what corresponds to deforming associativity constraints. That's what corresponds to these guys. Differential is thin minus thin is equal. So that's a differential. Okay. So psi is arbitrary indeed, but natural transformation. So psi is this endomorphisms with two variables, natural in two variables. So endomorphisms of two-fold tensor products. These are endomorphisms of three-fold tensor products, natural in each of the factors. This is endomorphisms of two-fold tensor products. So that's what these are. Endomorphisms of two-fold tensor products, endomorphisms of identity, just identity factor. One-fold tensor product is just the object itself. So endomorphisms of objects, but natural collections of such. And then the differential is the difference of these two, and it is equal to A prime minus A. So that is the, as before, that is the one morphism source and target equation. Only deforming associativity. So I'm really computing the tangent in this groupoid. So how do you compute the tangent in this groupoid? As before, I'm choosing an object above defines over dual numbers. Then I'm choosing the identification when I reduce to the original thing, and then I compare them by triples. So morphisms in this tangent thing are triples. Yeah, but the unit comes for free. Units come for free. So this is this is the only this is the only condition for deformation theory. With the unit, you really have this normalization condition. That's why, so normalization is free. You have to combine with that. That's much more interesting. You have to deform the underlying abelian category, and then it will be bicomplex. I don't want to talk about it in the talk, but yeah, there is a bicomplex. But yeah, it captures like affine things. Okay, so I'm not defining this complex, but you can define it yourself, right? So the differential from degree n to degree n plus 1, it's a cochain as before. It actually comes from a cosimplicial structure. This is a cosimplicial structure. These are cophase operators. As with Hochschild, again, where does this come from? Cosimplicial structure, this doesn't care about it all. But yeah, it is sort of very, very strongly there. So the thing you do is, okay, most of the cophase maps is just tensoring two neighboring things. This is a bulk, but then two extreme cases is when you use the identity on the last or the first of your objects, and that's like just very much like Hochschild. So that is a general differential, and we end up with a complex which lives forever. But the first, there is also the zero term, the cryptic term, which you cannot, but that requires sort of 3 stacks. Yeah, but the complex lives forever. Again, why? So maybe infinity, but no one bothered really to define even in this sort of very modest thing, just a infinitizing associativity, making the category infinity category and allowing for homotopy in here, and then the higher homotopies. What are high homotopies? Okay, stash of polytopes should be the answer, but no one has it written down. So that would be a natural framework for seeing the full complex as a deformation complex. I'm sorry, yeah, maybe after talk, so I'm running out of time. I have to. I'm sorry, just yeah. Wait, please wait 5 minutes. So the same hiccups, the same problems. It is coming with a bracket, but not degree 2. So Gerstenhaber bracket was okay. It's E2 algebra structure. It's a degree 1 bracket. But here, this the bracket you have, you can write it down, but it will be trivial because it is not E2, but it is E3 algebra. The deformation, abstraction to deformation theory, tangent cone, is controlled by the next degree bracket. And it really is E3 algebra structure, not just the bracket. It's like the Delinge conjecture for this cohomology, which is actually easier. So that was a joint work with Michael Batanin. It's actually easier to write sort of the full E3 operate action on this complex. Yeah, it's okay. Operate. Take the operate of little disks in dimension n. So you have configurations of disks inside big disk. And then you have substitution gluing a configuration inside another configuration in any of those inserted disks. And that is gives you algebras, so that can act as operates do, and gives you algebras, and they're called EN algebras. You can turn geometry into algebra by taking chains. But yeah, that's very ugly to work with, but that's like an easy answer. So there is an action of a nice model of that three-dimensional operator on there. So it's measure of commutativity. You can turn, if it's spacey enough, you can turn disks around, and that's so the two disks inside one disk is a picture for multiplication, but then you have commutativity naturally coming from the geometry, and then the more space you have to move the two things around, the more commutative you have. So this is topological, really nice topological way of seeing commutativity in its possible levels of strength. And that thing was, due to Gerstenhaber, was 2 commutative. This is 3 commutative. And the bracket, you could see even in characteristic 0, which was surprising. So in archive paper, we say, oh yeah, I couldn't find examples. Yeah, there are easy examples. You have to just drop identity objects, unit objects, and you have them. Yeah, drop rigidity. So the same sort of problems. Yeah, you have this nice, but yeah, EN algebra requires multiplication. So you have this picture of 2 balls inside a ball. It's a cup product, which from deformation theory is not visible, but it is visible from the interpretation of this as extensions. And extensions, yeah, what extensions are extensions in where, between what and what, are computed by this complex. Yeah, it turns out that it is like identity object and itself. So very much like in here, but the category is not the original one, but the its center, or a version of that. Bells are ringing, I have to stop. Yeah. We didn't order extensions looking at deformation theory. They don't make sense if you try to use this cup product to, say, manufacture 3 cycles out of 1 and 2 cycle. It's a mess. It doesn't make any sense, but it is there. So why? I wasn't asking for a video, but yeah, it can be made, but I wasn't asking. So there are like versions you can take and the functors which are bimodule. That will be, but I wasn't asking for a billion. My tensor are just k-linear. Oh, yeah. Extensions using this you can define anywhere. They are relative extensions, and so they are just exact sequences split in certain things. So really, you could went around all the potential obstacles with that. But yeah, it's yeah, in this basic sense, it's so much easier. Thank you so much. Thank you for your questions.